Hello and welcome to this video which is all about refraction. Refraction is a hugely important topic. In everyday life, refraction gives us the ability to be able to control the path of light. And when we can do that, we can make instruments like cameras, telescopes, microscopes, spectacles and so on. Light is a form of a wave, and many of the properties of light are common to other kinds of wave. So we can use some common school equipment to help us understand what is going on. We'll be using Slinky springs, a ripple tank, and maybe even a wave trough. This one is simply the diffuser off an old strip light, but you could use a standard laboratory tray. There are three main properties of light that we need to consider: the wavelength, the frequency, and the velocity of the wave as well. We're going to start by looking at wave velocity, and one of the best ways to demonstrate that is with Slinky spring. Eleanor is holding the other end and I can send a wave pulse down the spring. It's fairly clear to be able to see the pulse moving along. It's important that you only send a single pulse. If you send several pulses in succession, you'll get what we call a stationary or standing wave, in which the wave pattern doesn't appear to move along. And it's important for this application that the children get a grasp of what we mean by wave velocity, so they need to be able to see something moving along. This is what happens if you send too many pulses at once. And that's a very interesting bit of physics, but not what we want in this case. So for now, we stick with a single pulse. You could get the children to measure the velocity of that pulse. They'd simply have to time with a stop clock the time it takes the pulse to go from my hand down to the other end of the spring. Measure the distance, the length of the spring, and then divide the distance by the time, and they would get the wave speed. This would be a good time to talk about things like the speed of sound or the speed of light, to get the language into common usage. An alternative to using the Slinky spring would be to use a wave trough. We've got just a small amount of water in, and we've added a little bit of food colouring just so that the water shows up a little bit better. If I just lift one end of the trough, we can create quite a nice wave travelling down there. Again, it shows the pupils a travelling wave, and like before, we could actually measure the speed of that wave by taking the length of the trough, timing how long it takes the wave to travel the full length, and dividing the length by the time. To help pupils understand about the other two terms of wavelength and frequency, you could use the very good waves animation from the PhET simulation people. In this simulation, the waves are made by a dripping tap. You can turn the waves on by pressing the green button. What is nice about this simulation is you can have both a plan view of the waves and you can have a side view. Both views are important. The plan view helps us to recognise waves later on when they see them in the ripple tank, whereas the side view gives them a better understanding of what is going on because they can see the waves from the side, and it helps them to overcome the conceptual difficulties of seeing things from both angles. There is a slider so that you can change the frequency of the drops from high down to low, and it's pretty obvious on the screen what that effect is of having more drops per second or fewer drops per second. You can also freeze the motion by pausing the video and then using the measuring device to indicate what is meant by a wavelength by measuring across the distance from peak to peak or trough to trough or any two pairs of points. Right, okay, let's go back to the Slinky and have another look at an important wave property. I'm going to send a wave pulse down like I did before. Have a look at it and just make a note of how fast that pulse seems to be going. And another one. Okay. Now, I wonder, Eleanor, if you could send one that was faster. No, really faster. How about slower? I'm not convinced there is any change in the speed. I think maybe Eleanor changed the amplitude, and if she sent more than one pulse, I guess she'd probably change the frequency. But here's the thing. There is actually nothing that the wave creator, Eleanor in this case, can do to control the speed of the wave. The speed of the wave is entirely due to the tension or the nature of the spring. And that is true of all waves. The wave speed or velocity is only dependent upon the nature of the spring or the material itself. We could test this out by trying to change the nature of the spring. We'll send one more pulse along at this speed, and then we'll change the nature of the spring. I'll ask Eleanor to shorten the spring and stretch it out a little bit more. We'll see if the changed spring makes a difference to the speed. Okay, would you like to shorten it down and stretch it out a little bit more? Okay, now it's a different spring because the bit that we've got on the table is more stretched. Check this speed out. That's significantly faster. And if we now have the full length of spring but we shorten it, that's quite a bit slower. So the velocity of a wave depends only upon the medium that it's in. If we change the medium, we change the wave velocity. Okay, so now we're going to investigate the relationship between the three variables we've talked about: the wave velocity, the frequency, and the wavelength. We now know that the wave velocity depends only upon the nature of the material that the wave is in. That's the water, its viscosity, its depth, the sides of the tank, and so on. And there is nothing that I can do with my paddle to change the wave velocity. But I can change the frequency. I can make rapid waves at high frequency, or I can make low frequency waves. If I make low frequency waves, so not many per second, each one can travel quite a distance before the next one comes along. So I will get quite a big wavelength. But if I make high frequency waves, then each one doesn't get to travel very far before the next one, so I get a short wavelength. Okay, so here is another important demonstration with Slinky springs. We've already said that the speed of the wave depends only upon the nature of the material itself. So what would happen if we joined together two very different Slinky springs? Based on everything we've said so far, we might expect that the wave speed would be different on one spring to another. Let's see if that wave speed difference actually shows up. Okay, so let's just look a little bit more closely at what happens when the waves pass from one spring to another. Suppose I were to send waves down my spring at 3 Hertz. That's 3 waves a second. 3 waves a second would arrive at the boundary, and so 3 waves a second must pass onto the lighter spring. The frequency must be the same on both springs, because we can't create or lose waves at the boundary. But of course the wave velocity changes. So when those waves pass into the lighter weight spring, it will travel much further before the next one comes than was happening in this spring, and we should get a longer wavelength on the lightweight spring than we do on the heavier spring. Let's give that a go and see if we can see not only the change of speed but the change of wavelength as well. Before we can apply all of this theory to our understanding of refraction, there are a couple of conceptual difficulties for pupils that we need to help them get over. Up until this point, they've probably done experiments with a ray box, maybe with mirrors or maybe with glass blocks, in which they see light as a single path of light going across a white piece of paper. And yet at this stage now we're telling them that light is a wave. And children have a lot of difficulty understanding what that means when all they've seen is a single ray of light coming from a ray box. The ripple tank can help us to get the children over that conceptual difficulty. Shallow tank of water with a light source casting patterns of the waves on the dash below. At the moment we've got a straight beam strung across the tank on springs, being wobbled up and down by the motor. We're making what we call plane waves, straight line waves. Okay, so now we're ready to start applying all this background knowledge to our understanding of refraction. And what I've got set up in the ripple tank at the moment is the equivalent of when Ella and I had the two springs joined together. So I've put into the tank a rectangular piece of perspex because over the top of the perspex the water is shallower, and in shallow water the waves move slower. We're sending plane waves from the deep water into the shallow water, or in other words from where the waves will go fast to where they'll go slow. Based on what we did before, we should be able to see when we look at the waves underneath that the wavelength goes less when the waves cross over onto the perspex and they begin to slow down. If that's not immediately clear, you can take a still picture on your phone, and without the waves moving you should be able to see that more clearly. Okay, and so to finally make the connection between waves and rays, we can use this animation. The animation shows plane waves heading down the screen, mimicking those we've just seen in the ripple tank. I can then add the ray line. And so one way to explain this is that the waves are the things that actually exist, and the ray is simply a line, a construction line, which shows the direction in which the waves are going. So back to the animation, and this time the animation is going to show for light what we've just tried to show in the ripple tank. We're going to have light, plane waves, coming through the air and passing into glass, slowing down, just like the water waves did when they passed over the perspex block. And as the waves slow down, the wavelength should get smaller, which hopefully is what we also saw in the ripple tank. We can add the ray to show the direction of those waves. Okay, where this starts to get really interesting is when the waves hit the rectangular block at an angle. So this time I'm just going to rotate the block so that the plane waves come onto the block at an angle. And now we can clearly see that when the waves pass over the rectangular plate, they slow down and begin to change direction. If in the deep water they're going straight across the tank, when they get over the rectangular block, they are now at a slight angle and are coming over this way. And here we are back at the animation, again now trying to show for light what we've just seen happen in the ripple tank. This time the plane waves are going to come onto the boundary at an angle. When they get to the boundary and move into the glass, they slow down. They begin to fall behind that part of the wave which is still in the air and going fast, and so the wave begins to bend. They move across the glass at a different angle, and then when they emerge back into the air, they begin to speed up again and go back into their original direction. We can add the rays to this diagram, and even add a normal line at the point where our ray strikes the glass block. And if we now remove the waves, what we are left with is the diagram that we always produce when we do refraction of light with a ray box through the glass block. So there are many interesting effects which are down to refraction, and these are well covered in the textbooks. Things like mirages and why a pencil looks bent when you put it into a beaker of water. But when refraction gets really interesting is when we change the shape of that plate in the ripple tank. What we've seen so far is that when waves passed into the rectangular block, they changed direction. But when they came out, they changed back to going into the original direction. Okay, moved over slightly to one side, but the direction was the same. What would happen if instead of a rectangular block, we had a block shaped like this, or maybe like this? Now, when the waves emerge from the block, they will be going in a totally different direction. And by using blocks of different shapes, we can control where the light goes. We are heading into the territory of lenses. We hope you found that video useful, and thank you for watching.